Hello and welcome to our fourth video on shear turbulence. This is a continuation of our discussion of turbulence that's caused by surface friction, and now we're going to discuss how to fly in these kinds of conditions. So at lower altitudes, because of the strong shear, eddies are being produced, and these eddies are what causing turbulence at low altitudes. One thing you want to do when you take off in these types of conditions, under strong wind conditions with lots of big eddies, remember that these eddies can change your angle of attack. They have vertical gusts, and as we discussed in previous videos, those vertical gusts will change your angle of attack. If you're flying at a very low airspeed, that change in angle of attack may result in you exceeding your critical angle of attack. In other words, the aircraft may stall. So typically when you have strong wind conditions, you want to accelerate the aircraft to a higher airspeed before you rotate, and also perhaps you might want to climb out at a higher airspeed initially. Of course, all the turbulence is being generated down at low altitudes, so you want to climb to a higher altitude to get a smooth ride. In this case, it would be above the boundary layer. How do you know what the boundary layer is? In reality, you don't. You just keep climbing until you get smooth air on top. A lot of times, if you look at airmets, they will forecast moderate turbulence from the surface to 7,000 or 6,000 feet, and that pretty much tells you where the boundary layer is. As you descend, remember that there is a layer of turbulence, the boundary layer, and you need to slow down the aircraft so that you don't exceed the maneuvering speed. In that case, the aircraft will stall before it brakes or bends. Other things that you should be mindful of as you come in for a landing is that you want to, of course, maintain positive control of the aircraft, which means typically you're going to come in with a little bit higher power on final approach, and because you have a strong headwind, your ground speed is decreased dramatically. So you want to move over the ground probably about the same ground speed, which means that you have to use a higher power setting than but that you would normally use under light wind conditions. Also, you might consider the configuration of the aircraft. Configuration means flaps. Do you land with full flaps on a gusty day? Typically, no. You usually use partial flaps, but it depends upon the aircraft manufacturer's recommendations. Also, as we said, usually your ground speed is slower, so you want to have a higher airspeed on final approach. How high? One rule of thumb that's been used over the years is to adjust your final approach speed for the gust factor. And the gust factor we discussed earlier was the difference between the peak gust and the average or sustained wind. In this case, the difference is 8 knots in this METAR. Typically, you take 1/2 of your gust factor and add it to your final approach speed. If your final approach speed is 79 knots, 1/2 of the gust factor is 4 knots. We have a gust factor of 8 knots, so 4 knots plus 79 gives you 83. So adding 1/2 of the gust factor gives you enough buffer to avoid stall and also make a successful landing. As far as flight planning, what kind of things do you look for when you are flight planning for surface friction turbulence? Well, of course, if the wind speeds are great, then you know that you're going to have surface friction turbulence. Typically, a windsock is fully erect at 15 knots. If the winds are greater than 25 knots, then you're going to start to see turbulence over the ground. And we're talking about gusting conditions. If the gusts are more than 25 knots, then you're going to have turbulence. So how do you know what the wind speed is? Of course, looking at windsocks, listening to the ASOS or AWOS on the radio. METARs will tell you, and also the ATSC. You can also look at the surface analysis chart, look at the packing of the isobars, and that tells you how strong the winds are. And then as far as turbulence, you will get pilot reports of aircraft at low altitudes reporting turbulence or low-level wind shear. We'll talk about that in another section. But also airmets tend to forecast this type of turbulence, as well as SIGMETs for severe turbulence. And you can look at low-level significant weather prognostic charts to give you a forecast of turbulence at low altitudes.
Here is a case of strong winds blowing over flat terrain. This happened in June. You can see that there is a strong pressure gradient out ahead of a cold front and behind a warm front as a low pressure system starts moving across the northern plains. The graphical depiction of surface observations show that there are strong winds blowing over the ground. At Bismarck, you have sustained winds of 20, gusting to 30. Fargo, sustained 20, gusting to 35. And even in South Dakota, you can see that the winds are pretty strong there also. These are METARs from the afternoon, approximately 0Z and 23 Zulu, at Aberdeen, Bismarck, Fargo, and Grand Forks. And you can see the winds at Aberdeen are howling. The sustained winds are in the 20s at Aberdeen, 28 and 27, but the gusts are just phenomenal. 47, gusting to 47 knots, and also 44 knots at Aberdeen. Bismarck, similar with sustained winds greater than 20, but the gusts are up into the 30s, as is at Fargo, also gusting into the 30s and upper 30s. And at Grand Forks, the winds are gusting up into the mid-30s. Here are the terminal forecasts for those 4 locations also across the Dakotas. Remember, across the Dakotas, you've got generally flat terrain. So this is just the strong winds blowing over the ground. At Aberdeen, of course, they're forecasting to be gusting at 47. Notice that as the night progresses, the winds still do stay up. There's a pretty strong pressure gradient. And there is strong shear in the lowest layers of the atmosphere. So at the Aberdeen airport, you can see that wind shear is expected to be in the lowest layers of the atmosphere. Winds change by more than 30 knots from the surface up to 2,000 feet. At the surface, the winds are 18 sustained, and they are 50 knots sustained at 2,000 feet. So there's a pretty strong shear layer in the atmosphere, and that shear induces turbulence. Same thing at Bismarck. You've got, once again, strong shear there with also strong winds. The same with Fargo and also Grand Forks, with winds at 2,000 feet over Grand Forks blowing at 50 knots. This is a winds aloft forecast, a graphical depiction of it, and it shows that at 6,000 feet, for this time, 0Z, it's forecasted the winds to be 50 knots at both Grand Forks and also Aberdeen. So very strong winds across the Dakotas. Here is the textural product of the winds aloft, and you can see that at 6,000 feet it is, in fact, 50 knots. It's 49, so they round it up to 50. But very strong winds in the lowest layers of the atmosphere. As a result, they put out in the AirMet Tango, they put out an area of sustained surface winds greater than 30 knots just to the east of Bismarck and in Aberdeen's airspace right there. And then also across that region, as a result of the strongest shears in the lowest layers of the atmosphere, they do have a region of turbulence from the surface up to 8,000. So that's your boundary layer. And that turbulence is a result of just the wind blowing over the ground, mixing up, getting these little eddies, all these eddies, very energetic boundary layer, producing turbulence all the way up to 8,000 feet. As the winds start to decrease, I expect that top of the boundary layer will decrease, and you might see turbulence not to 8,000, but perhaps maybe 6,000 or lower. And then, of course, with the strong winds in the lowest layers of the atmosphere, they're also got a low-level wind shear advisory out for that region. So this gives you a little bit of perspective as far as strong winds over the ground producing turbulence. It happens anytime there's a strong pressure gradient. It can happen during the wintertime. It's more prevalent in the winter, but you'll also see it in the summertime too.